Okay, everyone, so I'm going to walk you through how I would solve this integrated spectroscopy problem that we did as a clicker on Monday. I presented it to you and we actually ran it as a clicker today, Wednesday, and you guys did very well with it and I was proud. Okay, so the first thing that I would do, given a molecular formula, is to calculate the degrees of unsaturation, okay? So degrees of unsaturation is equal to number of carbons minus 1/2 of anything that bonds one time. So that's your hydrogens and your halogens, okay? Plus 1/2 of anything that bonds 3 times. That's nitrogen and phosphorus, but I'm not going to have any phosphorus in any of these NMRs, okay? Plus 1. So notice oxygen does not physically have a consideration in this formula, but it is encompassed in this plus 1 over here, so you don't have to worry about the oxygen. Okay, so degrees of unsaturation for C9H1802 is equal to 9 minus 1/2 of 18, no nitrogens, plus 1 equals 1 degree of unsaturation. This is important to do at the very beginning when you have a molecular formula because I think it helps you contextualize what you might be looking for in the IR. If you have a degree of unsaturation, you're looking for a carbon-carbon double bond. You're looking for a carbon-oxygen double bond, okay? So those are the things that we would expect to be seeing, and we know how to identify in an IR, okay? But if you don't see either of those things that you should be able to identify in the IR, then it helps you think of a ring, okay? Because we didn't work on identifying rings in the IR because it's not a super reliable signal. And so if you calculate degrees of unsaturation, you can't find that there's a carbon-carbon double bond. You cannot find that there's a carbon-oxygen double bond. It's likely that you have a ring in your molecule, okay? So that'll help you. Also, if you find that you calculate degrees of unsaturation and you end up with, say, 4 degrees of unsaturation or more, I would almost immediately go into my NMR and look for signals in the 6.5 to 8 range, because if you've got 4 or more degrees of unsaturation, I bet you got a benzene ring, okay? Should be able to identify that in the IR, but you absolutely should be able to identify that by signals in the benzene region of the HNMR. Okay. Okay, so next, because I have some context here, I'm going to scroll down here and take a look at my IR, okay, and identify absolutely all the signals that I can confidently identify. Here, I'm going to draw my line at 3,000, or just look, and see that there's only signals to the right of 3,000, which means I only have hydrogen stretching on sp3 hybridized carbons. Okay, I see this beautiful carbonyl C double bond O signal a little past 1,700. Okay, I don't see anything else of particular note, but before I say ketone, which is these 2 signals alone, I need to make sure that I don't see any of those token signals for some of the other carbonyl compounds that, that aren't as simple as a ketone. I definitely don't see an OH stretch for a carboxylic acid. I do not see the hydrogen stretching on a carbonyl carbon of the aldehyde. That would be like a little blip right here, okay? Sometimes it starts a little bit lower and it would blip right here, but it's just this one little guy that looks like the CH stretch is going to end and then it blips down like that, okay? The only distinguishing factor between a ketone and an ester is the C single bond O. And if I look now in the fingerprint region to determine whether I have an ester here or not, between 1100 and 1200, I have this deep signal that's kind of got a thick base right here, like it's just kind of chunky. Even the little splits here are kind of have some thickness to them. Okay, that's your C single bond O that I mentioned. If I want you to see it, it's gonna be there. Okay, but even if you don't immediately recognize that or trust that, don't forget that you have 2 oxygens in your molecular formula. Okay, so you have to, but you only have 1 degree of unsaturation, everyone. So you have to have a C single bond O somewhere here. So then you can be confident that this is indeed what you thought it was. Okay, so I either have an ester, that's my most immediate thought, with this kind of an IR spectrum and 2 oxygens. My guess here is that this is going to be an ester of some sort, and my job is to figure out what arrangement of carbons is over here and over here. Okay? But you could also say that maybe you have a carbonyl and you got to figure out what's over here and what's over here, and you also have an oxygen that has some stuff on it, and you got to figure out what's over here and what's over here. Okay? For the most part, these HNMRs that you're going to be dealing with are going to be single functional groups and not polyfunctional groups. Okay? Unless it's a very obvious thing like an OH alcohol and an aldehyde or something like that. Okay, so I think that what I'm getting from this IR is that this is an ester. Okay? And I'm going to go ahead and build that. I want to go ahead and draw it because I need it to stay in the back of my mind that I have to build off of it. That's a structural component that I'm not going to get from the HNMR because there are no H's on it. So I need to keep that. I need to put it right there in my pile of things that I'm going to be building on. Okay? Then I'm going to come to the HNMR and I'm going to label each unique signal as A, B, C, D, E, F, and G. Okay? And I'm going to start analyzing with A. Actually, before I do that, one thing I want to do is count up my hydrogens. 3 plus 6 is 9, 7, 8, or 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that matches the number in the molecular formula. That should make me feel good because it needs to match. Or sometimes it could be exactly half, and that would be then a molecule that's showing you that it has some symmetry, where you really only have to figure out one part of it and then reflect it on the other side. But that's not the case here, and it really can't be the case here with an ester because you've got a carbonyl on one side that's bonded to a carbon, and then on the other side you've got an oxygen, so there's not going to be a plane of symmetry there. Okay? All right, A is a 3-hydrogen triplet. Okay, that tells me that I have a CH3, okay, and all of those hydrogens are my A hydrogens, and he's next to, if it's split into a triplet, that's 3 peaks minus 1 is 2 neighbors, okay? So I'm next to a CH2. I can do one of 2 things here, you guys. I can go hunting for this CH2 and continue building off of this until I can't anymore, or I could just jump over to B and try to keep coming back and remembering that I have this CH2 when I get down to the CH2s. My strategy tends to be that if I've already drawn it and I know it's there, I want to go find it if I can. If I can exclusively tell you which signal here is for these CH2s, or for these hydrogens of this CH2, I want to go ahead and label it. So I'm going to jump over to looking at D and E because they're my only 2 hydrogen signals. So D is a 2-hydrogen, multiplet resembling a quintet. What am I telling you? I'm telling you that there are 5 peaks here, which you could have counted yourself, right? 1, 2, 3, 4, 5. Looks like 5. So 5 minus 1 means 4 hydrogen neighbors. But what I'm telling you is that these are not equivalent neighbors, okay? Because if it was a pure quintet, I wouldn't have called it a multiplet. I would have just labeled it quintet. This is telling me that if you have 4 hydrogen neighbors, then you either have 2 and 2 that are different, or you have 3 and 1. Okay? All right, so I need to keep that in mind. I'll do this like it's a quintet, but I need to remember it's not a pure one. So somehow I'm going to symbolize that to myself. And then E is a 2-hydrogen doublet, and that one's a pure. Okay, if E is 2 hydrogens, that's next to, it's split into a doublet, so it is 2 minus 1, 1 neighbor. That's next to a CH, and that's all that's next to that. Okay? And then D is next to 2 different types of protons. And so because E is a CH2 that is only split by a CH, this CH2E cannot be this one. Okay, because that one's next to a CH3 and will at least be split into a quartet. Okay? So then these must be D hydrogens. Okay? Where if this is a quintet, then that means 5 minus 1 is 4 hydrogen neighbors. That means I have the 3 coming from A, and then next to that also I must have 1 more to get up to 4, because 4 neighbors plus 1 would give me that multiplet resembling a quintet. Okay? So now I can either go look for that CH, okay, and recognize that I also have a CH that's involved with this doublet, right, with E, okay, next door to E. These are E hydrogens. Okay, so now I'm going to look at my 1H's. Well, I've got a 1H. F is a 1H nonet. Okay, so that looks like a lot going on there. All right, and then G is a 1H sextet. Okay, so a nonet is going to be 9 minus 1 equals 8 hydrogen neighbors. Okay, and a sextet is going to be 6 minus 1 equals 5 hydrogen neighbors. Okay, so notice that if I'm trying to figure out whether this CH right here, over here, next to D, is F or G, then I really have to figure out which one of these splitting patterns it could possibly be. Well, right now I only have 2 hydrogens next to it. And if this was F, say, I'm going to put this in, let's see, I'll put this in a different color because it's tentative. If I called this F, then that would mean that ultimately that CH has to have 8 hydrogen neighbors. I already have 2 from D, and then another 3 and another 3 would give me 8. But now notice that's the end of the molecule, everybody. All the carbons here have 4 bonds. All the hydrogens have 1 bond. That's the end of this molecule, and I'm supposed to be able to put this stuff onto the ester functionality that I already have drawn. So that can't be the case. This cannot be F. Okay? This must be G, because it's my only other CH signal. Okay? And what is G next to? Well, G is next to 5 unique protons. A CH2, okay, a CH3. All right? And then notice that gives the carbon holding the G hydrogen 3 bonds. And so whatever is here cannot have any hydrogens on it. Well, what do I have that doesn't have any hydrogens? Well, I've got a carbon of a carbonyl and I've got an oxygen. Okay? Since G is the most shifted signal, I should know that G is the set of hydrogens that is closest to the most perturbing group or atom here, and that is an oxygen. So I know now that G is attached here. It's got a CH3. Okay, there's G. I've got a CH2. There's D. And I've got a CH3, and that's A. Now, the one I haven't labeled is I haven't located this methyl that I knew was there from the splitting pattern of G, but I haven't actually identified what letter those protons are. Okay, so now I'm looking for a 3 hydrogen. Ooh, next to 1 hydrogen neighbor, this is going to be a 3 hydrogen doublet. Do I have a 3 hydrogen doublet? I better hope so. because otherwise I've very confidently put this thing together and I made a mistake. Okay, indeed I have 1 3 hydrogen doublet right here. That's C. So these are C hydrogens, and I'm going to label those as such. Okay. So notice building, just starting at that 3 hydrogen triplet of A, I've built one whole part of my molecule and even figured out which part of it goes next to the oxygen, as opposed to which part of it goes next to the carbon of the carbonyl. Okay, now I've got to figure out the rest of this. Okay, so let's go back now. I've already done signal A is accounted for, signal B is not accounted for, signal C is accounted for, signal D is accounted for, and signal G is accounted for. All right. So now let's look at, let's go back down to what I have here. I have the CH2E hydrogens already labeled, okay? And since this is a doublet, notice guys that this is a doublet. That means that the only thing it can be next to is this CH that I already have drawn here. And the other thing, the thing on the other side of this CH2, must not have any hydrogens on it. The only carbon I have here left, or the only atom I have here left that can be next to that CH2 without any hydrogens on it, is the carbon of the carbonyl. So then I should know then that E is right here, CH2, and there's E. Okay? And that E is next to a CH. Which CH is that? Well, I only got one CH that I haven't accounted for. G's already accounted for on the other side of the molecule. I've got this complex multiplet resembling a nonette. That's supposed to be 8 hydrogen neighbors. Well, that's going to be right here. If I've already got 2 hydrogen neighbors accounted for, then I need another 6, okay? The only way I'm going to be able to distribute that and not violate any octets here is to put one of the methyls here on this carbon and then another methyl on that carbon. Okay? All right, so now again, F is split into a nonette by 8 neighbor hydrogens. These 3, these 2, and these 3. Okay? Now, if that takes care of E and that takes care of F, and then I've actually put in 2 methyl groups here that I have not labeled, and luckily I end up with B as a 6 hydrogen doublet. A 6 hydrogen doublet, everyone, 6H doublet. If you came at this from a different angle, then maybe you figured out earlier that you had this isopropyl type thing, okay? 6 CH3 bonded to a CH bonded to another CH3. That's a 6 hydrogen doublet, okay? Now, it doesn't mean that this hydrogen can't be split by something over here, and it is in this, but that part of it, that 6 hydrogen doublet, is a quintessential peak for this group right here, okay? And so these are B hydrogens now. And one thing I like to do, if I hadn't been so careful throughout this whole thing of putting this together step by step and labeling as I built it, I would ask, should it be next to the oxygen? Should it be next to the carbonyl? If I hadn't been so careful, what I might do is I'd throw this thing together in a way and then go in and try to justify each signal, because we've already done that. We've already started with a structure and went back to or predicting what the signals would be and what the splitting pattern would be. So if you build a structure and you have enough time, you can go back and make sure each of those signals you would justify as what's showing in the HNMR. And then there's really no denying that your structure fits. It fits the number of unique hydrogens, it fits the splitting patterns, and it fits the chemical shift. I can't ignore one or the other. They're all equally important for getting the correct structure. Okay, so my correct answer here for this is this isobutyl group attached to the carbonyl, and then the oxygen attached to a sec-butyl group. Okay? Here's my A hydrogens. Okay. Here's my B hydrogens. Here's my C hydrogen. Okay, all of those are methyl groups. That's why they're kind of far on the right. Even if I'm creeping towards the oxygen, I'm still the most boring of all of these. And I'm not directly bonded to the oxygen, so my shifts aren't very affected. Okay, or the shift that you expect me to have. Then I go to my CH2s. There's my D, and there's my E. Okay. Those are, now E, notice, is further shifted than D because E is next to the carbon of a carbonyl, and D is simply not next to any perturbing group or atom. Okay, he's getting close to that oxygen, but the proximity to the carbon of the carbonyl is going to be more perturbing than just a couple of carbons away from the oxygen. All right, and then finally I have my most shifted signal, which is this CH, and I expect that to be the most shifted because that hydrogen is on a carbon that is directly attached to the oxygen, which is the most de-shielding atom here. All right, everybody, I hope that helps. If you come at this a different way and you still got the right answer, not some variation of the right answer, but the correct answer through and through, don't change your strategy. You just have a different way of approaching it, but you get it. Okay? If you got very close, but you mixed up the groups, then that means that you're not paying attention to the chemical shifts. And the chemical shifts relatively should be able to tell you from one, help you differentiate one isomer from another. Okay? If you've got something else that doesn't look like mine, but looks that you really just feel in your gut, you can match up with every signal, I'd love to see it. And love to talk to you about whether that would be a valid structure for this spectrum or not. All right, thanks.